We need new energy sources in the world. We need sustainable, we need renewable energy.
Fossil fuels are running out, and our use of them is releasing greenhouse gases into the air and polluting Earth's atmosphere. Our world needs sustainable and renewable resources to be our sources of energy. It is predicted that we will run out of oil in 50 years, natural gas in 70 years, and coal in 250 years. By that time, humans will have done irreversible damage to our planet's ecosystem. The main sources of renewable energy are wind, sun, rivers, and the ocean. This issue is going to be impossible to ignore in our lifetime. To address it, we need to look towards finding creative solutions. Frank Sargent has been a part of that mission.
In Professor Frank Sargent's paper on Biorecovery of Precious Metals from Wastes and Conversion into Fuel Cell Catalysts for Electricity Production, he discusses how using proton exchange membrane fuel cells made from a particular strain of E. coli have the ability to produce hydrogen and be used as a fuel cell catalyst in the powering of things such as vehicles and electronic devices.
Making a fuel cell is you need electrodes that are very reactive, great catalysts, and these are made of precious metal, palladium, platinum. Again, suddenly we're into expensive things that are short supply, not sustainable. So one idea we came up with is how can we recycle palladium from the environment?
Palladium is malleable and can absorb up to 900 times its volume in hydrogen. For those reasons, palladium is a great metal for the catalytic converters in cars. Using fuel cells to biomanufacture used palladium offers a route towards sustainable energy.
A proton exchange membrane fuel cell is a type of fuel cell that contains a special polymer electrolyte membrane. This allows it to operate in situations with a lower temperature or pressure when compared to a regular fuel cell, making them very useful in niche situations. As well as this, they are a promising alternative to the aging alkaline fuel cell technology. In the diagram, you can see fuel and air entering either side of the central membrane electrode assembly, as well as hydrogen entering from the left and oxygen from the right. This reacts not only to produce water, which is indicated in the diagram with the purple arrows, but an electrical current is also produced, which is indicated in red. To complete the cycle, we can see excess fuel exiting the cell on the left, and excess air, water, and heat leaving the unit on the right.
The fuel cell is driven by a bacterium, in this case an E. coli mutant, to produce an active palladium catalyst. A catalyst is a substance that changes the rate of reaction while not changing the outcome of the reaction. Usually, a catalyst is added to decrease the activation energy required for a reaction to take place. If push-ups signify the rate of reaction, then by adding a catalyst, in this case putting your knees on the ground, decrease the energy needed to do a push-up, and the amount of push-ups, the rate, increase.
And the idea was that we could use a bacterium to take this waste palladium-2, which is oxidized black dust, and then to reduce that, just to, let's say, recover it into base metal. So take some waste, turn it into pure metal, valuable metal, and make that into a fuel cell.
This research can be built upon and enhanced to improve and expand on solutions to fossil fuels and our aim for renewable